Good evening, ladies and gentlemen. My name is Greg Nolan. I'm an Associate Professor with the School of Architecture and Design, Australian name, for the discipline of Architecture and Design, because we have been amalgamated. Anyway, welcome to tonight's presentation. This evening, we're very pleased to have Professor Christoph Sigritz with us. Christoph is a visiting fellow at the University of Tasmania at the moment. So he's with us for 3 weeks now, and he's with us then for another 2 months later in the year. And he's come over specifically, because he likes Australia and likes to drink red wine from Australia. So there's been a bit of that. But he's also come over to work with us to develop timber research, timber engineering capacity at the university, and also then to establish greater links between his own institution, which is the Basel University of Applied Sciences, and UTAS. So we're very pleased to have Christoph with us. He's one of the leading researchers in timber engineering internationally. And I've asked him specifically to give us a talk on advanced timber structures from Europe and what they're seeing as cutting edge, so that we can see if we can deploy similar things here. So the arrangements this evening is that we'll have basically about a 30-minute session. We'll have a break for tea and coffee. Then there'll be another 20, 25 minutes after that and questions. We'll try and finish it all up by 8 o'clock. Okay, so I'd like to introduce Professor Christoph Sigritz.
Okay. Now my mic is on. Can you hear me? Okay, good evening. Greg, you forgot the beer.
I forgot the beer.
Yes, you forgot the beer. So it's a pleasure for me to be here tonight. Thanks for coming. I think there will be slightly longer 30 minutes and 20 minutes talk, but I can always stop if you think that it is going to take too long. Okay, let's get started. These are the topics I'm going to talk about to give you a little insight on what we're doing over in Switzerland, starting with small buildings, going through a couple of designs, and discuss then in the second part a case study on complex timber structures. For us in Switzerland or in Central Europe in general, timber engineering is a kid's play. It's easy for us. We do a lot in timber and we have a lot of expertise. So here, just to start with, a little example of a playground for kids built in timber. Let's have a look at some small buildings, as these ones here. This is a building from Switzerland. The idea is to have an autark building, which just includes everything. And the idea is also that you can place these kind of buildings at any location you like, so you can move them around. You can move them by helicopter, for instance. And the idea is that everything is in there you need for living, like the resources. You need electricity, you need water, you have waste. So you try to get around with all these border conditions, and this gives a very small, compact, but also in an architectonic point of view, very nice structures. This is an example from an architect from Madrid. Same idea, as you can see, very lean construction, very simple kind of architecture. Everything is in there. You can see the two hooks which are used to transport the building on a different site. Of course, all the footings are temporary. You can have something like screwed footings or temporary small concrete blocks. That's all quite easy to do. Another example, we do quite a lot of bridges, be that for traffic, normal traffic, or especially for foot traffic, bicycle tracks and stuff like that. Here, a crossing over a 4-lane highway, very simple solution. Basically, what we have here are two walk-in trusses, nicely covered bridge, very good for protection against moisture, water, direct water. I think this is the way you have to build. Also, there are some barriers around here, which are nicely protected. So these layers, you can replace them if you need. inside view of such a construction. You can see the trusses, very simple. It could be all in timber, but in that case, to make it a little bit more slender, they use here some steel rods for the hangers instead of taking or using quite big cross sections in tension. So very simple structure. On top, you have this battery of glue laminated timber to support the roof. On the bottom, you would have the same system being attached to the bottom girder of that truss. So pretty straightforward solution. I think one of the things which is very important in timber engineering are, of course, the connections. And you can see here some typical type connections, which you would find in many structures. So if you can, you have some connections where you go onto contact. The connection between the secondary beam to the top girder of the truss would be just a very simple bracket connection. This is a bracket which you won't find off the shelf, so it has been designed on purpose for that. And what we use then is some small diameter dowels on double shear to make these connections. We also try to use the materials where they are appropriate. So, for instance, on the portal on the front, to take all the horizontal reactions from the bracing on top and on bottom is realized here in steel, because you get smaller cross sections. You have heaps and heaps of resistance out of these cross sections. So there's no point to use at these locations, for instance, a solution in timber. And it makes, of course, the appearance of the whole truss very slender. Another example of quite a nice bridge, you can see that bridge here. It has a span of 30-odd meter. This bridge was prefabricated, or let's say the members were prefabricated in a workshop, and there was a temporary workshop, as you can see here, built just turned 90 degrees to the bridge crossing, where all the pieces are delivered. Everything is ready to be mounted. It's all quite nice, light stuff. Of course, you might need some cranes to move them around. But so the whole bridge was pre-assembled here on that side, covered everything on it, and then the entire piece, as you can see it here, weighing something like 360 tons, was put in, 130 tons, sorry, was put in with a big mobile crane on its setting. So very interesting way to do. Advantage of timber being, of course, sometimes the weight. Here again, you can see some connections. Everything is hidden. We must provide long durability. So the roof is one part of the concept. The second concept, of course, is the cover on the side to avoid that the rain is directly going onto the structure. And then all the connections are made in a way as already seen before. So there's some gaps between the secondary and the main system in order that the timber can dry out if, in case there is still some water getting onto there. This patch here is basically finishing the connection. You could imagine that in here we have some glued in steel rods and steel plates, a steel connector, which allows to connect the two pieces together, and then you either route or with a resin you protect the entire connection by this simple means. So I think these are quite efficient, very nice structures. This is quite a new building that has been built on top of the Prealps in center of Switzerland at an altitude of something like 2,300 meters above sea level. All the structure has been brought in by a cable car, which is actually servicing this top location. This building has been designed by Herzog de Meuron. The architects amongst you certainly know these guys. They're looking at perfect solutions. Everything is designed through from A to Z. If you look, for instance, at the line of these rafters here, if you stand in front of it, there is no, there's just a line. It's not plus minus half a centimeter or a couple of centimeters. It's really precise and very neat. So the big challenge here was actually to bring or to prefabricate this structure in a way that it could be brought up by cable car and put on site. So of course there was on site, there was a crane in the end, but so the big challenge was basically all this planning, prefabrication, transport, and all the logistics you would need for building in such a place at such an altitude. On top of that, of course, winters are quite long, probably a bit less long than in Tasmania, where they go from November to October or something like that, or just 1 month of decent weather, but in similar case in Switzerland. So pretty long winter and short construction period. Very good foundation conditions, of course. This cantilevering block of concrete carrying this timber structure. An inside view of the big area for restoration. So there's a lot of thoughts about fire safety at these places. There's a lot of thought of acoustics also, having many people eating in here. The floor, for instance, was also a special development because in wintertime, all the people come in with the ski boots to drag in a lot of water, a lot of snow, and a lot of moisture. So the floor has been made in a way that it can basically eat up this moisture content, but give it back later on in order not to be deteriorated whilst using. So very nice timber solution, very simple also. So good, neat architecture. It's actually quite trendy for the moment. We have a lot of alpine clubs, and these alpine clubs have actually a lot of old existing clubhouses in the Alps. And of course the problems are, how do you build? In these altitudes you have all the problem with wastewater, with energy, and so on. And this was a project, and it's the Monte Rosa Alpine Club hut, which is looking like a crystal. This concept has been developed together with ETH Zurich. And that's just a big autark structure where you can live within these environments. And here again, of course, construction period even shorter. We are looking here at an altitude of something like 3,600 meters. So it's quite difficult to build in this kind of conditions. Inside views, it's a kind of a rotating structure. You can see some trusses which form separations, and also some new tools being used to decorate. So it's some CNC working of the timber structures just to make it more look like timber. But basically this is also one of the concepts which are very important for all the structures I'm showing you. See they're all very neat, very clean, hidden connectors, and of course all the structures you will see are very precise, and this is one of the key issues we are looking at in Europe to get this level of precision realized also for timber structures. This then allows, of course, in a very short time to set the structure in place. This is another good example, a little viewing tower, something like 35 meters high. This was a project we developed at our school. So it was a student semester project where we collaborated, or where the students collaborated between architects and engineers. So there was one architect, two engineers developing a project, and we did some pre-designs of this project. In the end, it was realized by the same student who had this idea as he was working in one of the better glulam factories in Switzerland. And the trick here, as you can see, it's not on a high altitude, but there's no way that you can come in with big trucks or cranes or whatever. So this structure, for instance, was actually prefabricated in the factory, in the timber yard, where they put together the structure elements like this. So these elements were built one after the other, and in order to make sure that there's a 100% fit, a first element was built, the second element was built, then the second was built or put onto the first one to check that everything was okay, numbered, and then flown onto the site. So the whole operation to build the tower you have seen before took something like 8 hours of helicopter work, putting together the entire structure. The advantage, of course, of such things is that you don't need scaffolding. We need scaffoldings for towers. There are other examples that have been realized in Switzerland. Well, these scaffoldings, if you're looking at 35-meter high towers, they cost 60,000, 80,000 Swiss francs, and this would be quite a substantial amount. Of course, flying helicopters is also quite expensive. The minute is very, very expensive, but in that case, it turned out to be much faster and cheaper to do rather than going on site with cranes and trucks. Let's have a look and start looking at some industry buildings. I think some of the important things you need is you need some decent material to build with. And one of the decent materials, of course, is glulam, very important structural product we use very, very often. You have seen many projects already before, these nice square cross sections. You only get them if you use glulam. If you use sawn timber, you will have the cracks due to seasoning. If you want to have nice and constant aspects of the timber, glulam is certainly one of the favorites to be selected by the people doing these constructions. Here, this is a building with a span of maybe 23, 24 meters. This was for the WTA Women's Tour in tennis. This building is actually just sitting next to our school, which is part of the same school or University of Applied Sciences, so it's next to architecture, timber, and civil engineering. There's also a sports school which forms people like Roger Federer, and they are pretty successful, as you know. So this fellow is here. It must be something like standard. So up to length, we can produce length up to 32 meters, height up to 2 meters high, tapered, curved, whatever you like. And I think this is a prerequisite to be able to realize structures in a cheap and efficient way. All the rest, so mainly these guys here, a bit special. All the rest is more like the standard carpenter know-how, building these wall systems, putting the bracing in, designing also the columns or looking after the columns which are good enough to take the forces. In the end, this building will be an industrial building from the outside. You're not going to see anything from the inside. It looks like any other boring building, red facade, in this case in steel, because it's just the cheapest way and the most efficient way to get it done. You could, of course, do it also in timber. It will be more elaborate. There will be more maintenance. These kind of products, of course, are quite interesting to be used for simple solutions. Let's have a look maybe in a little bit more detail, not just showing heaps and heaps of pictures. This is a very new building, which is very special because it's a carpentry setup for medium-sized carpenter who is prefabricating homes. The special thing is that this factory is going to sit in the middle of a residential area with very restricted access to get there, to bring in the materials, to bring out the prefabricated homes. The second interesting thing is that these guys wanted to have one and the same building for producing these homes. On top of it, they planned the office of that company, and the next level apartments to be rented out. And of course, this gives quite a lot of thinking to be done in terms of the living and working in the same place. So you have to care about acoustics, you have to care about vibrations, noise, and so on. And so this was the big challenge in these buildings. Also, this is a very innovative guy who wanted to be a little bit at the upfront of the developments. We are not that much used to work with hardwoods. Our main species is spruce. It's a softwood where we do all this glulam and sawn timber which we are using for our construction. So for the moment, there's a huge hype in hardwood structures, and the species we are looking at is beech. And now the people start to producing also glulam, solid timber in beech. So this guy actually tried to use this new material in special ways to get some innovation done on his construction. So this is the building as it is finished. You can see here residents just next to it, so they don't want to be bothered about noise and stuff like that. This bottom part of the building is going to be, or is the factory where all the production takes place, offices on top, and living further up. Very simple timber facade in this case here. So in this construction as well, some of our students would participate in developing like the layout of the factory, looking at truss systems for spans, again, of something like 24 meters, and also in particular looking at hybrid structures, combining steel and this beech hardwood to high-strength columns, with the goal that maybe they would have a similar kind of size as in for a concrete column. If you look at these systems, you can take a lot of load on that. So this asked for some tests and development and calculations and optimization, and the guy was interested to use that in his factory. So you can see here this column prefabricated, nicely covered. Beech is known to suck in timber as much as possible, so you have to protect these fellows from the rain when you're building. So here again the columns, and another thing which is very important and gets more and more important is to be precise. Usually the concrete guys, they're plus minus 3-5 centimeters, which is not precise enough. So we had to take all these tolerances by other means. So for instance, looking at positioning this steel box here, which will then take the footing of the column, as the column has to be vertical and be at the precise position. It must be spot on at plus minus nothing, if you like, because afterwards you will put in between prefabricated wall systems and stuff like that, and you have to level out your building in a nice way. So here, for instance, they exercised also this new techniques called BIM, which is nearly a 4-letter word in Switzerland already, because everybody talks about BIM, but nobody's doing it. So here they tried really to interact, to have this data. So for instance, leveling out this piece was directly controlled by the programs going via this measurement device here. So you can see here a closer shot of these columns. So basically, the column finally will be a triple member with grooves to the side of the member so that you can place your rebar. This rebar will, of course, in the end be linked with adhesives to the timber to have a composite action. And at the bottom of the support to have a fixed moment connection. Some additional rebars I can see here, or threaded bars, are also used to take the force and bring them into the steel plate. In this case, in order to have a very strong connection, that steel plate was in the end welded onto that box, which is, as you can see here, already cast into the concrete footing. So a very efficient way of doing, and very high capacity solution, which is of course gives new ways of building. The spans are not that big, but as on top you have a couple of stories bringing all the loads onto the main load carrying system. On these columns there was quite some substantial load. So you can see here the columns again. Piling up the columns, it's important that you have end grain connections. In this case here, even replacing a direct contact between timber with an additional steel box where you can connect the secondary members here also in steel to facilitate the erection. So these floor elements would slide into these I-beams, and you can have very easy solutions for the floor. You can nicely connect it also to these I-beams to have diaphragm action and stuff like that. Well, I think this is the most important thing you can see here. So even the crane, overhead crane they have in there, something like 10-ton crane, is running on a timber beam. You will get a lot of vibrations and dynamic action on the building, which you don't want to feel when you're sleeping on the last floor. So there's a lot of effort has been undertaken to actually disconnect this system from the rest of the building. Nice little detail introducing by contact these quite big forces coming from the overhead gantry. This fellow here was also part of the development. You would like to have on the bottom, in the first floor, an open space to have all your activities for building prefabricating homes. So you need this open space. So you need big spans. And there have been some calculations, as there are a couple of stories on top with substantial weight. So they developed these big trusses, which are, again, like in that timber bridge, walk-through trusses as part of the building. So this element here has the height of the next story. Here again, they used in some parts, they used hardwoods for the highly loaded diagonals. You can see no connectors in there, but of course everything is connected. In this case here with glued-in rods, which are, from an aesthetic point of view, of course, very interesting. Well, we have some people who know how to do that. You have to do that, of course, off-site in the factory where you have the good conditions. All the support details in order to stack that element onto the timber columns or the beams is all in already. You lift it up, you position it, and this will be the final view then from the interior. There you have the trusses giving the height. You have the top chord of the truss and the bottom chord where you attach the secondary elements. Everything prefabricated as wide as you can to have it easily installed. Not many things to do on site. So basically, of course, there's some tools around, but not many. It's all done or prefabricated in a way or to a level that that is nothing to be done on site actually. And this would be the final view. You can see here these trusses. So these trusses are not full trusses. It would be preferable, of course, to have the truss linking at the node. So we get some bending moments here. So that's why probably also these fellows are quite big. But there was we need some space to go through. So this is the office part of that building, where actually the structure matches quite well with the usage of that office space. Of course, it stands maybe a little bit in the way. It's not an open space, but in an office you don't need that necessarily. However, on the bottom, this is then the look into the factory, which is operating now. We will have here again the bottom truss at the bottom chord of that truss, which is sitting above, ensuring this big span. And you can see the nice layout with all the materials, all the machinery which you need actually to prefabricate homes. So they will, of course, build finished elements which they then transport to the site for a new construction. This is just another shot. You might also see that these workspaces usually are quite nice and clean. The messier places, you could maybe find this in glue line production because they are working with adhesives and stuff like that. But in these places here, you want to have precise solutions. You have a neat way to work with the materials. And then this would be the reception area well, these trusses here are fake. They are not belonging to the truss because there's one section with columns, post and beam solution, and just one, the major part, which has these trusses as load-carrying members. Okay, multi-story building is something which is very current. People are trying to do them here as well. So in Switzerland, this is also a big issue. This kind of, everyone is trying to break the record of the highest building, most possible stories. But I think the big market is in something like 4, 5, 6-story buildings. And at least in Switzerland, we are not allowed to build that much into the height. It is changing now, but in Biel, for instance, where our school is sitting, we are limited at something like 5 to 6 stories. This is a Shigeru Ban design, which is part of a big development by the Swatch Group. You know all Swatch watches, and Hayek, who is the owner of the Swatch Group, and he wanted to have a timber building. And here again, we are looking here at the building where they assemble watches. And that means that these workspaces you must have zero vibration. And this is a very big challenge because every construction material is kind of softish. You have your floor systems, so even badly executed concrete floors or steel floors, they could be too soft. And that was a very big challenge here to be solved, because here in these areas you have just office or workplace after workplace where they assemble the watches. Unfortunately, they put down the blinds, so you cannot see the timber structure mainly, but it's a very simple post and beam timber structure at the inside with a kind of a curtain facade in glass all around. This is the head office of the Swatch Group going on. Again, a 5, 6-story building. It's all in timber. And you will see afterwards the structure which goes above, on top of that, will be a very interesting free shape structure, also developed by Shigeru Ban. And this structure is going to be completed in the very near future. You will see some slides afterwards. Well, apparently Shigeru Ban is very well known in Switzerland, and people like to work with him. This is another Shigeru Ban building. It's just by chance. This is Tarmedia building. So a company that does prints, so for newspaper journals and stuff like that. And Shigeru Ban actually developed a system for that building which works with solutions that are only made in timber. So there are no steel connectors in here. Looking at a hinged connection, for instance, you could have this hinge, for instance, in steel and a lot of steel plates all around, and the solution they were looking at here was to have a timber connection with this kind of oval or elliptical connector. So that's not a hinge anymore. It gives you some moment restraint. That means that you have frames which are built, which is very good for static purpose. Very simple erection, and that would be the building as it is realized in the end. It's like with bones. Basically, the main part, in order to put all the bending moments or whatever, can be quite slim, but where you have the connection, there is some effort to be taken. You might need some larger cross sections, especially when you're looking at pure timber to timber connections. So very interesting stuff. Here again, everything prefabricated, 100% precise, and it can be again erected by a crane and cherry picker, and there's not much to do. You just see a little bit a view of that connection, because there's so much force going through that you cannot work anymore with our spruce solutions. So here is a multiplex plywood with plies that are turned 30 degrees, one next to the other, which gives a kind of very uniform, homogeneous block of timber, which can take the high lateral pressure which you will get when you connect the forces to that member. So locally, you can see has the timber been reinforced at this location. This is another trend. Sometimes people don't want to build straight away a 6-story building. So here, this is for ambulance and police, the headquarters in Bern. The building is actually conceived to have 6 stories, but for the moment they only built 3 stories. So if there is need in the future, or if someone buys this building later on because they're going to move to a different place, these guys, and the this office will be used for other purposes, or this building will be used for other purposes, there had been quite some thoughts to have a design which allows also for multiple usage afterwards. So for instance, the floors were designed for more than the loads they have now in this building, to make sure that if someone afterwards comes in for a new usage, that the timber or the building can still be used. So that's also quite an interesting approach. I think it's quite an expensive approach. You never know what comes after that. And but strengthening an existing structure is also not very easy to do. You can also see some other techniques which are used very often, like concrete, timber, composite systems, which is also something very interesting. Connections here again, very nice. Here they also used hardwood columns because we have very high loads, having the 6 stories above. This is another trend we have in Europe, looking into hybrid structures. Not everything has to be in timber. Some projects, it could be interesting to look at placing the material at the perfect location. So in this situation here, they used steel columns. At some places with bigger spans, they use precast concrete columns. Steel I-beams connecting to concrete to have a composite action steel and concrete. And in the other directions, timber, which gives you composite concrete timber floors. So this would be a shot through the section of the floor. So we have these I-beams with the standard connection in order to have at this location the concrete steel connection. Then they have used prefabricated vertically laminated floor panels with a little offset in the board. So they have actually worked with 2 boards of different depth. This is for the looks when you look underneath, but it's also for acoustics. This gives a very good surface in terms of acoustic. You don't need any further insulation or panels, as you can see here. Here you see the grooves and the rebar, which then make the composite action between these vertically laminated panels and the concrete. Very easy system, very simple, but of course it's quite special. It's a new development that you have systems that span in 2 directions. So far, you would mainly span in one direction because getting away with negative moments on the supports is not that easy. You have to make sure that the compression goes somewhere through here, but in casting in the concrete here at this place, that works. Just some shots how this is realized with the bolts connecting to the steel. Very simple installation of prefabricated, roughly 1 meter wide panels. That is easy to do. You can see the grooves here again. For the composite action, there are some screws in there just to make sure that there's no uplift between the concrete layer and the timber layer. Then comes the rebar. You pour the concrete, and you have your very interesting high strength and with very high stiffness composite floor. The spans are quite big in this case here. And then you go for the next story. And from underneath, this is how the offices look like in the end. Here a shot from underneath. You can see this plus-minus profile, as we call that, which is very good for the looks and very good for the acoustics. It's quite interesting also, if you have this vertically laminated timber, you might have some concrete grout running through, but if you water, for instance, the top surface, it will swell a little bit, it will close up the gaps. You don't need any plastic sheet, you can directly pour the concrete on it, and you don't have any concrete liquid dribbling through your system. If there is, you have to clean it. yeah, we don't want to have dirty members in there. And so on. I think we don't have to discuss that too much, but in Switzerland now they're also looking at 8 to 9 story buildings. So we have quite easy laws in terms of fire safety and stuff like that, going up to the high rise, which is around 24 meters, which allows you to build 6 to 8 stories without any big troubles. Of course, there's always a concept you have to establish in terms of escape routes, non-combustible materials, and some places you might need a sprinkler. So these things people, architects or the engineers discuss with the fire authority. And then it's the same again. So here you can see apparently this is working quite well. High strength columns using for the vertical load transmission, for horizontal load transmission, composite, timber, concrete floors. We have in Europe a new material that has appeared lately, which is beech LVL, which is a hardwood LVL with extreme good strength properties. So they do like big panels, but from these panels you can cut like beams and columns in the size you would like, in the width you would like. Sometimes you might have to patch them up sidewise in order to have your final section. Okay, that was my first part. Do you have questions on this before, after the break, we go on with some complex timber structures? Yes?
Base plates. Do you say that the base plates on the foundation are welded to the...
Yes. Usually, earlier you would say don't weld on site because you never know what you get. But now for some of these connections, it is much easier to weld. If you have connections. Mechanical connectors, you need double plates and you need spice and you need whatever gear to make it fit. But in this way, it was just easy putting down the column. Exactly. As you must be level because there's no way to. You can maybe patch up a little bit, but not much. Maybe 2 millimeters or whatever if the column is not 100% perpendicular. But there's always the big discussion. Do you want to also to have recesses in the concrete? For instance, you have a concrete core and you have to attach in one way or the other the secondary system. So you can provide openings to fit in whatever, or you can provide already cast-in steel members which have very complicated connection details, which is then again not very handy for the concrete. Form working, right? Because it's in your way. So people start actually having flash surfaces with all the insets required, which are already in there, and then come level and do some minor welding on site. But of course, you have to be careful and make a good job. Yes?
How deep are composite floors?
It's 240, 280 millimeters around there, or whatever you need. But the composite floors, they're good if you span from 6 meters above. Probably the best area to use this is around 8 meters. And then you would have typically something like 16 centimeter vertically laminated or a laid down glulam beam. And on top of that, you would put something like 8 to 10 centimeters of concrete, which gives you then 16 plus 10, 26. It's around there.
All right, Christoph will be coming out to have a cup of tea as well, so you can grab him then. So we just keep it to about a 15-minute turnaround. So tea and coffee's down here. We've had to import teaspoons because there are no teaspoons in Antarctica, and therefore there was none in this building. So there's tea and coffee down here, water, there's a couple of apples there, just knock those off. Toilets are on the right-hand side, and there's the hot water, instantaneous hot waters just in the little tea room bay, just a little bit further down. and we'll get going again promptly at about 1:30. Okay, thank you.
Yep, okay.
Oh, one other point. Tonight's lecture's being recorded, so we will put this talk online probably by the end of the week.
Okay, now here we go. I think you should put it on again a bit. All right. Okay. Good. Okay.
How's that up?
Good on the back? Okay, let's go on. Complex temper structures. The things that I've shown you before is kind of boring stuff. Everyone does, and of course needs a lot of know-how and technology and so on. But I'd like to present you some very new fields where a lot of research is being done now. This is what we had already a long time ago. So if you look at the date 1983, they already built domes with 160 meters diameter in free cantilever method. That is that could be done. A very nice swimming pool area where the structure is already getting much more complex because you don't have a dome. You have a dome with cut-ins. You marry various domes together, and what you end up in the end is with very static, very complex structures, and on top of that you will get curved members, and these members will be curved in two directions, and this is really difficult to be produced. But people have already done that in 1986, or this structure here, which is a recycling area. At the base, 100 meters diameter, and this tower, which is the chimney, which is also the support for this tension structure, was something like 80 meters high. The interesting thing is that these structures, they were actually built with the first issues of design programs. Before that, everything was done by hand, and at that time, ETH Zurich, for instance, they started developing computer tools which would allow to do static calculation. And I did my thesis at ETH, looking at if it was possible to design dome structures, for instance, by hand or not. And the conclusion was it's all fine unless you have vertical loads, but as soon as you have non-symmetric loading, you're just stuffed with hand calculation. So we need these tools, and it was quite amazing actually that they could do this at that time already. And the key basically for doing that is that there's a very high constructive competence within the carpenters. We trained them for 4 years, and it's a good training. The know-how of the engineer, of course, is very important, and everything was done in just using very simple models in order to get this geometry and these shell structures. And actually, I remember that for this hanging structure, they checked the deformation, and the deformation was within 20-30% of what they actually expected. It was even a bit stiffer than they thought. And another thing was also that basically at that time, we didn't have engineered wood products. We had only straight members or beam bar members and boards, but not big size panels, for instance. This is all new. So no software, no large size panels, no cutting centers. CAD/CAM was not existing then. Everything was done by hand. All the drawings were done by hand. And if you couldn't draw it, you would build a mock-up and try to find a solution. Very interesting. And so people would only focus on some items. For instance, in that case, they would focus on how can the engineered timber structure be built. That was the main focus. And maybe there were some requirements in terms of something like fire safety, building physics, not important, vibration, not important. People wouldn't look at that, okay? Just take the most important issues and try to find a solution. That was the approach then. And so basically what they used were either short, simple elements complex connections in order to play around with the geometry, but everything was basically quite simple. And still today, this is what we do. What we have, of course, in Europe, we have state-of-the-art design tools. We have standards. We have Swiss standards, which are very similar to the Australian standard, which is also similar to Eurocode. But in these standards, we have a lot of information, a lot of help to do a correct design. And what we have today now is a very big range of solid timber, glulam, engineered wood products in terms of panels, which can have big width, extreme big length. So it's getting much easier to actually build structures, or also complex structures. There are also a lot of people developing systems like Lignatur. They would have like panel members, but which are built up by single boxes. So with all the solutions, how you can connect them sidewise, longways, how you do the detailing and everything. So there's a lot of knowledge around. And of course, the big companies, they also have CAD/CAM. They can digitalize their structures. So we're getting in an entirely new kind of world. So this is, I remember, it's a church building. This is very simple, basically, because if you look close, all the members, they are straight, or maybe they are kind of slightly curved in only one direction. And the key here is that you have a solution for the detail that works so that you can build that structure, but it's not very, very complex. It's still a demanding task if you want to model this and to check and to get all the internal forces and so on. But it can be realized even by companies which are fairly small. Sticks and putting the sticks together. Now the challenge we're looking at is multiply curved, free-shaped structures. You might have seen one or the other. Again, Chigoruban, sorry, maybe you should come up with good Australian architecture, and then we'll have some Aussie designers behind. A straw hat, which gives this kind of shape to the Centre Pompidou in Metz. So this is a real free shape structure, actually covered with textiles. So even covering with textiles is not that easy. You need a pattern, like for a clothes for a lady, for instance. You cannot have curves covered with square panels. That doesn't exist. So already this is a huge challenge. In terms of timber construction, this is not too difficult to do once you have the geometry, because all that structure is built up by layers. So we have basically in always two members running in one direction. So we have three directions, and we just pile up, or in this case, the roof is built in piling up horizontal lying members. The trick is basically to get the connection, and the connection was very complex because you have to start from the bottom. You sit on a scaffolding, you put the first layer, and you have a connection sticking out. You put the second layer, then you have to extend the connection, put the next layer, and so on, to be able to erect such a thing. And if you're looking at the single members, of course, we have fellows like that, which not many people can do. There's one company, Hess in Germany. They start doing this kind of double bent members in working with small squares, because a board, which is say 35 mil thick, 120 mil wide, you can bend it only flatwise. You cannot bend it sidewise. And in order to get the bending on the other side, you also have to work with 36 mil, okay? I have no idea how they put the things together, because you have to put pressure on both sides. You have to put the adhesive on and everything. So this is the secret of the company. What people do usually for that is to have a kind of a pre-shape where they first produce a beam that is bent in one direction, then they cut it up in the other one and reglue it and put the curvature in the second direction. And if the geometry doesn't fit 100%, they start milling it down to the final dimension. So this is the way how they do it. Again, sorry, Shigeru-ban. This is that building. We have seen that building on the back. This is a 5-story timber building, the headquarters of Swatch. And there is this reptile or this snake biting into that building, which is a 100% free-form structure. Looking a bit closer at the end, it's all very secret. Nobody has seen that structure from the inside or was allowed on site. They make a big secret out of that. But this is the kind of members we have. If you look at these beams, they're all composed vertically by 2 sections because we have in this situation lap joints. That means you cut out on the bottom member half of the timber, and on the top member the other half of the timber, so that they can insert and get the connection. So for instance here you see there's one piece missing which comes on top. So you put first this one here and then the other one comes on top, and you have to make sure that you can slide it in into these gaps there, and also you need some connectors in order to take the shear forces. And I don't remember how many members. I think there were something like 2,800 members. Not one member is equal to the other one. They're all different, and every member has to be designed specially. This is a huge task, of course, and I know that the guys who produced this structure, which is Blumer Lehmann, they managed to do something like 80 pieces per week. That's all. And every piece, before you manufacture it, you have to check if the geometry, curvature, everything is right. Very big task, because on site, if it doesn't fit, it doesn't fit, and you have to go back to the workshop. The only thing they did sometimes was some sanding, because it would not nicely feed in. So putting away a 1/10 of a millimeter or something on the surface, and then you can slide it in and do the connections. So it's very, very complex work. So closer look here, and you can see how this member intersect. You have to think about what part of the member is continuous, where do we have the cuttings. What they try to do is basically to have not more than maximum 3 points to connect one piece on top of the other, because then the degrees of freedom are reducing very, very much, and you might not be able to erect it. And this is the kind of structure they built. So you can see this member here, for instance, there's a joint here, and this member goes over to somewhere here. So, and this is one part of the structure, and everything has to be produced prefabricated. There was a question before at what moisture content these things are produced. They're produced at 12% plus minus 2.5, difference of 5% maximum. Everything is produced today in the shop. It's delivered at the end of the week. Let's say these 85 pieces, they are delivered, and they're straight away put into the structure. And as you can have seen before, the structure is always covered. So you avoid having moisture content. If moisture starts getting into that, you can forget about assembling that stuff. It must be really, really dry, otherwise it doesn't work. And then this is the structure, how it looks like in the end. Unfortunately, they don't put a nice translucent cover on that. The idea is that it looks like a crocodile or a snake formed by scales. The information from the guy who was looking after the production was also that this surface, or every surface of a scale, is about 2.5 by 2.5 meters. So they try to optimize the size of these openings. And so the various covers, they have, some is textile, some is solid, some is window, which gives then the final aspect of that structure, which will be opened pretty soon. Now this structure here looks at high-tech, extremely high-tech, not necessarily super high-quality timber, but a big problem is that you're cutting the fibers, and you have to do some precise design, and you might need some really good quality timber, and very, very complex. And the problem is, you will see in the end is that most cases you don't get this shape in direct gluing, so you have to do a lot of milling. So what you do is basically you produce a big block and you start milling, and you have a lot of waste. So there were some guys at ETH Zurich, Gramazio Kohler, architects, who were looking at digital fabrication, which actually took a completely different approach. They only work with boards. So you can see here a truss. This truss has a certain geometry, but the geometry changes from one layer to the other. So maybe this diagonal at the next level is just twisted around a little bit, not having exactly the same structure. What you can see here is a robot that is running on something like 40 times 12 meters working surface. Here are all the boards. So this guy gets the boards, goes here to the cutting station, and at the cutting station, the precise length is cut. They are working with a certain number of board sections, and the robot brings then the member to the right place and connects it. The only guy you will see in that fabrication yard is the guy sitting here at the control center with a tie and suit. Nobody's putting one single hand on that entire structure. So here you can see that robot, and as you can see, the difference to the first structure is the first structure is defined by the connection, which is actually given by all the pieces which interconnect. So the connection point is defined by the cutting outs, okay? But here, we are going to put that a bit more to the left, a bit more to the right. It's skewed, so the robot is the only one who knows exactly where to put it. He does also the check if it's the right position, if the thickness is correct, and then it nails these connections automatically. You can imagine also the routine to determine the nailing pattern, starting from that point and knowing that every nail is going to probably 2 or 3 sections, and you don't want to hit the nail on the section below. You have to consider that there are some spacings between the connectors, so you have to parallel to the grain, perpendicular to the grain. You have to fit it all in, or you can work with a minimum surface required per nail. So to write this kind of routines that it works everywhere is probably a huge work already. And the interesting thing is, you see, this is just normal timber. So this is longitudinally finger jointed, solid timber in various sections, not a particularly good quality. But in the end, you have a huge family. You have a system with a system effect. If one of the fellows here is a little bit weak, but it doesn't matter, the fellow next door probably takes the forces. This is then the concept of this type of structures. So this is one prefabricated element. You can see that you get the curve in that way. You get also a movement in this way. So they produced heaps and heaps of these elements. We did some testing at our school to find out if the requirements in terms of strength and stiffness were met. The critical points here are actually the connections. So that was a special focus. So we would test 5 or 7 typical trusses which multiply a certain number, so different spans and different height. That's what we were testing, just to make sure that it works. And in the end, this is the structure you get. So all these elements are brought onto site, and they sit on a steel structure and give this wavy form on the inside. So the trusses you have seen are running in this direction. And of course, with playing with a number of boards and having openings more or less and stuff like that, you get this kind of view. And I think this is a very interesting approach. The only thing is that no human could do that. It's impossible, because finding the position of where you put your board, in what angle, you need some tools to do that. And this is the final view of that lab. I think this is a very interesting approach. So what we have been looking at for the moment in this approach is in just stacking. Actually, they come from brick. working. They wanted to have 3D brick walls where every brick is turned by 0.5 degrees compared to the previous one in order to have nice free shapes in brick walls. So they spent a lot of time, of course, to develop all this, and then they started stacking timber. So this is the simplest way of stacking timber. Maybe Australia should start at this place for the moment, and maybe glue it together, and then you have a glue-line beam. You can also, of course, connect it mechanically, which is not a very good idea because you lose so much of the stiffness, so you need the adhesive. But let's say for special structures, you could do that, or you have longitudinal connection, or you have, let's say, laminar layered assembly. You can also have the same thing curved, but so this would be the Shigeru Metz solution, where you just have the layers and the boards go in whatever direction, and they're free in space. They're curved, but you can curve these fellows very easily. And the new approach is basically to go now into 3D. So that means that these positions or these connections here, they are not known in the location, and the robot is again used to build such structures. So you can see a robot here who is assembling a structure, just a free shape structure. So here you have some tools to grip your member, and here again, this fellow here, the position of that one is not given. Right? There's not a connector sticking out where you know that it has to go in that hole, or that you have a slot in the piece of timber with a bracket which goes into that slot of timber where everything is defined. Here you have full freedom, degrees of freedom. So the computer or the robot has to know in what angle, what position he has to put that. So these were previous stages looking at tolerances and stuff like that. So the tolerances can be managed, but if you start, of course, doing some cantilevering structures, this is like a Solix system where you have one continuous member, one continuous, and then one continuous, but always a kind of displaced a little bit. You can already do very nice free shape structures. That's so. Step by step, the routines were investigated, how to assemble the things, and how to work with the system, and of course tolerances, because in the end you would like to have no tolerance or little tolerance. Maybe just a word to this Shigeru snake building. On 100 meter, they were out of tolerance, I think 5 millimeters, and across 20 meter span, 0. Which is not astonishing, because if you would have a tolerance, you can't put that thing together. That's the trick behind. So, because everything is so tight, it's 100% precise. But in here, because you have so many degrees of freedom, the tolerance is quite critical. So what you need is a digital data model, which has all the information on the connection, on the length of the piece, on the cuttings and the end. And from that, you can then talk to the robot who assembles a 3D structure, which is then done. And here you see all the operations at that stage. We are already a bit further now. So the robot grabs a piece of timber. It cuts it to length with the right angle. We also had routines in trying to find out if the piece is more or less heavy, you have tolerance in the arm of the robot. And if the piece is not nicely centrally held, it might rotate. So there's a lot of studies to be done that. But once he has gripped it on the right location, then you can do whatever drilling, additional operations on it, and then the robot places it. While here, still some hand working done, but the idea would be that this would also be done maybe by a second robot. And actually that in that roof you have seen with this truss system, they have then robots which are hanging from the top. And the next step is now that 2 robots can work together to assemble these kind of things. And that was a structure they built in the end for an exhibition in the Zurich main station. This is the size that robot that was available could do. So maybe something like 5 meters high and certain diameters. But it was, so the geometry was actually built by the robot, and some students or some people would just put some screws by hand. And this is a little bit what we are looking at. We had seen here in the first things when we were looking at complex timber structures, we just focus on very few items. And the question is, of course, is that actually good enough, or could that be improved? And now we have so many tasks to fulfill, building physics, for instance, or vibrations, or earthquakes. So there are so many big core areas which we have to start to interconnect. And for the moment, it is rather so that we have maybe a specialist in fire, we have a specialist in building physics, we have a specialist in developing structures, and we still have the problem of talking to each other. And in the future, it will be that we have a big box. Everything is dependent on the other on the other direction. We have to link between concrete, steel, and timber and try to find the good solutions. And we have the interactions between all these big core areas. And the question is, of course, is this a good way to go? Is this just kind of some show-off solutions? Or is there really a market or an interest to do that? And it could be that you have a kind of an overkill of the situation, producing things which you don't really use. I think most of that has been said already. But this might be a question afterwards for those who would like to stay on. Is it worth to do that? This is what we do today much better than it was before. I think you can dig in your boot box and find a lot of very interesting old-fashioned or old-style or traditional structures which basically do the job. But here, there are of course some new windows which open. Now to finish, just a short commercial. We are a specialized school in Switzerland forming structural engineers and product engineers, only focusing on timber. This is very interesting, and I think we are basically the only school who only does that. There is another school in Germany who does it partly, and a school in France who does it also partly. Otherwise, timber engineering is, as for instance here, is taught in 1 or 2 semesters, 2 hours per week or something like that. But our guys, they start first semester going through the studies, and they will be impregnated with something like 60% timber thinking, timber working, doing drawings, doing products, whatever. And we have now a very new master program, which is actually held in English. So if you would like to come over and study with us, it's very cheap, by the way. Enrollment fees is, I think, $900 a semester for everything. So $1,800 per year, which is nothing compared to here. It's one course which costs you already something like $3,000. So it's really cheap. Life is cheap also in Biel. It's not more expensive, I can tell you. The beer I buy at the local brewery is probably cheaper than the one I buy in Salamanca. Anyway, interesting for you guys maybe are the CTS, complex timber structures, where we have some 2 very interesting topics. One is a case study here, which is multi-story buildings, where we look at specific cases or situations which are critical, earthquake, for instance, where our students, they get some earthquake ideas just with replacement forces and stuff like that. But in here, they would do also the response analysis and all that, and really to do it with a modeling of the structures. So the case study would be something like a 6-story structure. We can do that new, or we can also analyze an existing structure. So this is the second big box here, which is assessment and retrofit of existing structures, also going through routines for earthquake, whatever. How do you have to improve the acoustics, this and that? How do you have to improve fire safety? Because it's a complete different situation if you're building on something existing or improving something existing or building from new. This is running now. We just accomplished this one here, which is focusing on free form and shell structures, where we have a very interesting case study. For being able to do that, we have here some electives. So you have to know CAD drawing, So you have some programs, you have to be able to model the structures. So you have to know Rhino to get Rhino or Grasshopper to get the geometries. So there's a toolbox which is done. We are doing something in finite element modeling and stuff like that, just to get the starting knowledge to do this this approach. This is a structure which is going to be finalized very shortly. This is the Cambridge Mosque, which is again a fully 3D free shape structure. This is the artist view, and the students had to find out what is the best geometry in terms of architecture. How can that geometry be described? How can this geometry then be optimized in view of static reasons, to minimize bending moments, for instance, or to share or to redistribute large normal forces? Then they had to think about, during these two processes, how could I possibly erect that structure? So thinking about the processes. And the last point they had to do is to think about manufacturing, and they had to manufacture a node, and that was that node here, this one here. Just 3 bars, doubly curved, twisted, pain in the neck if you want to find out how you solve that stuff. So this is the basic geometry. Already this, to find out the geometry, what is the reference? Is the reference the bottom surface? Is the neutral axis? Is it the top surface? The surface we would like to get is like a baby's bum, smooth, round, no kinks, no gaps, okay? And to do that, they had to divide the structure into two. There was a bottom part, which was kind of just a trunk coming up, which is very easy to do. It's rotating, a bar that is rotating around, so all the members are the same. And then comes this free shape structure. And then they had to model it and do static calculations. So this poor guy probably had quite some nights work on. What you can see on the back is the static model of that structure, comprising something like 20 or 24,000 members, with all these nodes. So this is an intersection of 2 bars, right? Which you have to put somewhere in the computer, and you have to check that the geometry is right, and you must follow the surface you have developed in terms of architecture. So not an easy task. So this is just a model of one lap joint connection. We have the neutral axis of the member. So one member is cut from top to bottom, and the other from bottom to top. In doing this, you create eccentricities, all right? And these eccentricities will create additional bending forces in the members. So in order just to have you see that this is the initial neutral axis, then you have the cut-in, and you have the displacement neutral axis, and then you have the top member, which is modeled. In order to be able to connect the connecting points, you have to divide these members by 2 and things like that. So this creates that big number of members. Another thing they had to think about is that I was trying to highlight before on this Shigeruban building in Metz. You might not be able to do this double curved member in piling up boards, even in splitting it up and doing it in 2 directions. So that's why maybe you have to build this black mother piece and then route it down to the dimension you need in the end for your member, which is the red one. So you have to make sure that you have enough meat around your bone, and you create a new problem. And the new problem will be that this member here, the grain is not following the boards anymore. So because of routing, you will have some cut fibers in the end, and you know that there's a big reduction of strength when you start having fiber to force deviation. So the students had also to work with routines to find out in what section we have what kind of fiber deviation, and it was limited to 5 degrees, something like that, in order to make sure that the design will work in the end. So lots and lots of work they had to do. This would then be the final node they wanted to produce, like the static model, with two important factors. These are the vectors of how you have to bring in your member. There's only one possible way that you can have this triple contact connection. So once they had that, they would go on the machine, so they feed the data to the machine, and they route the piece. So here we use some solid timber or some glulam timber, I don't know. Simplified thing, but already how do you put that piece on? It's impossible to route it from both sides. So you do one side first and then you do the other side. So you have to turn it around and stuff like that. So very complicated. And I think this student in the end was quite happy that he has the thing. So you can see that they're all curved, these members. They're twisted. And there's just one way to put it together. I once had some visitors. I took it apart and wanted to show how to put it back together. Impossible. Probably a little bit of swelling or shrinkage, and then it wouldn't work. So this is what we're doing, but basically I'm just showing with all these steps. These are the steps the guys have been doing on the swatch building, for instance, or in other free shape structures, and it needs a lot of handwork. So the guys who are kind of determining the size or the shape of one member, they have to really control step by step, member by member, connection by connection, every piece. So that's why they cannot produce more than something like 80 per week. Okay, so we do also that in a very short form with architects, because we want to get them thinking in this type of structures. So that was the same approach, simplified, find a solution. The idea was a round table. The people sit around and you can have like a European Commission discussion in there. So every student has a small slot, or group had a small slot. There were all the different designs, and it was then in the end, so the model. Once you have this model, they had to digitalize the models in order to get the connections, because here again, so that was one of the models they did. This frame here, once you have digitalized these connections and you have built it, you just stick it together like Lego. There's just one way how you can put it together, and you get the frame finished. And so we didn't push it too far. So we had just two sections and lap joints, and then they would put the screw in there just to make it work, and then put it in place. And that was the final solution of that. Okay, so that was my input. Don't think that you can get to that stage within 2 or 3 weeks or 5 months or whatever. There are many people having worked hours and hours and years, and there are huge research programs on the back. But of course, I think the interesting part would be for many people is trying to get at the right level into such systems and try to catch the rolling train. Okay, thank you very much for your attention.
Okay, so we've got time for maybe 1 or 2 questions for Christoph.
Sorry, 10 minutes over.
It sort of reminds me of the Gothic cathedrals, so all the roof work that went into that.
Like Gaudi or company, yeah.
Yeah, all that kind of stuff, and the only disadvantage of those is that there's no tension.
Yeah.
Stone, no tension. So with timber, similar thing, but there's actually tension.
Yes.
Well, so, yeah.
Well, timber is okay in tension, that's fine. Because the compression tension, of course, a bit less tension. But these members, because of the connections, they're pretty much oversized. So normally it is not a problem to bring the forces through it. The problem is more the connection, and at the location where the connection is, that you might have two big stresses. But that is the good advantage. I showed you this tent structure with the central thing. The initial design was a concrete solution, basically, which is completely stupid, because concrete is working well in compression, but in these tension members, there's only tension and bending moments, and that is the worst you can have in concrete. So Natural, at that time, he changed it into a timber structure, and timber works very well in tension. You have to be a little bit careful with grading and stuff like that, but when you start using glulam or other systems where you have some load sharing and system effects, then you can have a good solution.
One more.
It also looks like the internal hull on the boat, would the expertise from boat building
Yes.
be built upon to develop this?
Yeah, they did it already before that by hand. So the oldest boats were even built with naturally curved felloes, which they had from a tree, so curved trees, or they would maybe bend it with heat in order to get some curvature out. But this is the same start, and the boat is a perfect example because it's also free shape, and you're quite lucky because two members are the same. So every section changes and could be applied for that too, yes.
All right. Well, I'd like to wind it up. I think the important message from Christoph there at the end is that, you know, what he's shown you is the result of hundreds of people spending quite a lot of time to develop a whole range of capacity in a population of about 300 million. We don't quite have all those resources. Pardon?
The population is like 300 million.
Yeah, but when you look at the whole of Europe, because there's a lot of European.
Oh yeah.
So, but I think there's been a lot of improvements in timber construction technology entering into the Australian design professions over the last couple of years, and there's likely to be a hell of a lot more coming in the next 3 or 4 years. I think there's a lot of opportunity for particularly practitioners like us to learn from people who we can get out here, who can show us how we don't have to take 20 years to catch up, because we've got 20 years to catch up. But maybe we can do it a little bit quicker. So I'd like to thank Christoph for his presentation, and thank you all for coming.
Yeah, thank you.
Thank you. Good night.
If you have questions, I'll be around to build back the installation. I have to send this. This was the guy in the middle there, huh? Rod. You wanted to have the email address.